So, for today, let us discuss a complex topic that involves two diagrams, which is called the diesel cycle. But before we dive into the equations and problem solving, let us first know what is diesel cycle. Diesel cycle, also known as the constant pressure cycle, is defined as a combustion process in which the burning of diesel fuel takes place, and charge receives from the burning of diesel fuel. The only difference between the diesel cycle and the Otto cycle is that in the Otto cycle, heat addition occurs at a constant volume, while in diesel cycle, heat addition occurs at a constant pressure. According to Earthpin, this is how diesel cycle works.
The piston moves down, creating a partial vacuum, while the intake valve opens, drawing air into the cylinder. The piston moves down up to the bottom dead center, or the lowest point on our stroke. Second is a compression stroke. Now, the intake valve is closed already, and the air is compressed by the piston up to the point where it reaches the top dead center, or the highest point on our stroke, and the pressure and temperature are enough for combustion. Then, the fuel injector sprays an atomized fuel. Third stroke is the power stroke. As the fuel absorbs heat from the compressed air, it will vaporize, and boom, there goes your combustion. The combustion will force the piston to move down, rotating the crankshaft and of course your car's wheels. The last stroke, or fourth stroke, is the exhaust stroke. The high temperature and high pressure and burnt gases from the combustion will then be evacuated from the cylinder into the atmosphere through the pressure difference of the cylinder and atmosphere, and the movement of piston going up while the exhaust valve is open.
When studying the diesel cycle, we also need a PV and TS diagram just like the Otto cycle, but the process is different. Here I am going to explain the four processes involved in this diagram. First is the process 1 to 2, known as the isentropic compression. It means that during compression the entropy remains constant, and there is no flow of heat out of the cylinder walls. Here the air is compressed, so the pressure increases from P1 to P2, volume decreases from V1 to V2, temperature increases from T1 to T2, and entropy remains constant, which is S1 equals S2. Next is the process 2 to 3, known as the constant volume heat addition. In this process, the hot body is kept in contact with the cylinder, and heat addition to the air takes place at constant pressure. The pressure remains constant at P2 equals P3, volume increases from V2 to V3, temperature increases from T2 to T3, entropy increases from S2 to S3. Then after that is the process 3 to 4, known as the isentropic expansion. In this process, after heat addition, the expansion of air takes place isentropically, and work is obtained from the system. The pressure falls from P3 to P4, volume increases from V3 to V4, the temperature falls from T3 to T4, and entropy remains constant at S3 equals S4. Lastly is process 4 to 1, which is called the constant volume heat rejection. In this process, heat rejection takes place at constant volume. The pressure decreases from P4 to P1, temperature decreases from T4 to T1, entropy decreases from S4 to S1, and volume remains constant at V4 equals V1. Now that we know how this diagram functions, we can move on to the thermodynamic analysis of the diesel cycle, or formulas that we can use to solve different problems, which are the following. Number 1 are the formulas for state properties. For finding the temperature, temperature 2 is equal to temperature 1 multiplied by R raised to K minus 1. Temperature 3 equals temperature 1 multiplied by RC multiplied by R raised to K minus 1, or, it could be temperature 3 equals to max temperature. Temperature 4 is equal to temperature 1 multiplied by RC raised to K. And temperature 3 over temperature 2 is equal to volume 3 over volume 2. For pressure we have pressure 2 equals pressure 1 multiplied by R raised to K. Pressure 2 equals pressure 3 equals max pressure. Pressure 4 over temperature 4 is equal to pressure 1 over temperature 1. For volume, we can use volume 1 over volume 3 is equal to volume 4 over volume 3, or if there is a given temperature we can use temperature 3 over temperature 2 is equal to volume 3 over volume 2. For us to find the R or the compression ratio, the formula is max volume over minimum volume equals to volume 1 over volume 2 equals to 1 plus C over C. For the formula to find C or percent clearance, the formula is volume 2 over volume D is equal to volume 2 over volume 1 minus volume 2. The formula for the cutoff ratio or RC is temperature 3 over temperature 2 is equal to volume 3 over volume 2. And lastly, for the RE or expansion ratio, we have volume 1 over volume 3 is equal to volume 4 over volume 3. Number 2 is the formula when heat is added, which is QA is equal to change in H is equal to M multiplied by Cp multiplied by temperature 3 minus temperature 2. Number 3 is the formula when heat is rejected, which is QR is equal to change in U is equal to M multiplied by Cv multiplied by temperature 4 minus temperature 1. Number 4 is the formula of cycle net work, which is W net is equal to QA minus QR is equal to M multiplied by Cp multiplied by open and close parenthesis temperature 3 minus temperature 2 open and close parenthesis minus Cv multiplied by temperature 4 minus temperature 1. Or we could use W net is equal to M multiplied by R multiplied by temperature 1 over K minus 1 open and close bracket K multiplied by RC minus 1 multiplied by R raised to K minus 1 minus RC raised to K minus 1. Number 5 is the formula of cycle thermal efficiency, which is nth is equal to open and close bracket 1 minus 1 over R raised to K minus 1 multiplied by RC raised to K minus 1 over K multiplied by RC minus 1 open and close bracket multiplied by 100%. Lastly is the formula for mean effective pressure, which we have two, which are PM is equal to W net over VD is equal to W net over volume 1 minus volume 2 is equal to nth multiplied by QA over volume 1 multiplied by 1 minus 1 over R. The other one is PM is equal to pressure 1 over K minus 1 multiplied by K multiplied by RC minus 1 multiplied by R raised to K minus 1 minus RC raised to K minus 1 all over 1 minus 1 over R. Now that we know the different formulas, let us give a sample problem. 1. An air standard diesel cycle has a maximum temperature of 1800 K. At the beginning of compression, air is at 95 kilopascals and 300 K. The mass flow of air is 12 kilograms per second. For a compression ratio of 25, calculate a. The net work of the cycle in kilojoule per second, b. The thermal efficiency, c. The mean effective pressure in kPa. In order to solve this problem, we must first identify the given factors. T3 equals 1800 kelvins, T1 equals 300 kelvins, P1 equals 95 kilopascals, M equals 12 kilograms over S, R equals 25. The specific heat capacity at constant pressure of air at atmospheric pressure and room temperature is Cp equals 1.01 kilojoules over kgK, and the specific heat capacity at constant volume of air at atmospheric pressure and room temperature is Cv equals 0.718 kilojoules over kgK. Next, we need to identify what is being asked or required in the problem. A. W net, B. Nth, and C. PM. Now we are ready to solve. Let us begin solving by finding the missing state properties. T2 equals T1 multiplied by R raised to K minus 1, then it will be equal to 300 multiplied by 25 raised to 1.4 minus 1. Then we will get T2 equals 1087.17 K. RC equals T3 over T2. Then it will become 1800 K over 1087.17 kelvins, getting a value of RC equals 1.66. T3 equals T1 multiplied by R raised to K minus 1 will be equal to 300 multiplied by 1.66 multiplied by 25 raised to 1.4 minus 1. Then we will get a value of 3 equals 1804.70 K. T4 equals T1. multiplied by Rc raised to k, and will be equal to 300 multiplied by 1.66 raised to 1.4, and we will get a value of T4 equals 609.92 K. For the pressure we will use P4 over T4 is equal to P1 over T1, and when we plug in the values given we will get P4 over 609.92 is equal to 95 over 300, and after deriving the equation and solving we will get the value of P4 equals 193.14. Now let us find the heat added, which is the QA. QA equals M multiplied by Cp multiplied by T3 minus T2, and it will become 1.0062 multiplied by 1804.70 minus 1087.17, and we will get the value of 721.98 kilojoule per kilogram, which will be our QA. Next is the heat rejected, which is QR equals M multiplied by CV multiplied by T4 minus T1, and will be equal to 0.7186 multiplied by 609.92 minus 300, and is equal to 222.71 kilojoule per kilogram, which is our QR. Now that we have the heat added and heat rejected, we can now solve for the net work of the cycle. So W net equals M multiplied by QA minus QR will be equal to 12 kg per second multiplied by 721.98 minus 222.71 kilojoule per kilogram, and we will get the value of W net as equal to 5991.24 kilojoule per second. Now to solve for the thermal efficiency. Nth is equal to open and close bracket 1 minus 1 over R raised to K minus 1 multiplied by RC raised to K minus 1 over K multiplied by RC minus 1 open and close bracket multiplied by 100%. When we put all that is required in the formula we will get the value of Nth equals 69.15%. Lastly, the mean effective pressure. So we have PM equals QA minus QR over V1 multiplied by 1 minus 1 over R. To solve for V1 we have V1 equals RT over P equals 0.287 multiplied by 300 divided by 95, which we will get 0.91, and that is our volume 1. Now we can solve for PM. PM will be equal to 721.98 minus 222.71 divided by 0.91 multiplied by 1 minus 1 over 25, and we will get the value of 571.51 kPa. To recap what we solved, we have the values W net equals 5991.24 kilojoule per second, Nth equals 69.15%, and 571.51 kPa. And that concludes our topic for today. I hope you gained some knowledge regarding diesel cycle. Thank you.